Welcome to the Explainer. So, have you ever just casually hit send on a message to someone on the exact opposite side of the planet and wondered how on earth it gets there instantly? Seriously, it's basically pure magic. But today, we're diving into the actual invisible magic that allows a tiny piece of data to travel so seamlessly across the globe. We're going to decode the incredibly complex language of networks by exploring the foundational blueprints that make the entire modern internet possible. Okay, let's dive right into this. Imagine, just for a second, a world without standardized rules. What if a Dell PC literally couldn't speak to an Apple iMac? If every single manufacturer just went rogue and created their own distinct networking models and proprietary rules, a Dell would only understand another Dell, and an iMac would only understand another iMac. They'd be speaking completely different languages. In a global network, that is a massive, massive problem. To actually connect the world, we desperately needed a universal translator. So here's our quick roadmap for today's explainer. 1. The language of networks. 2. The 7 OSI layers. 3. Packaging data through encapsulation. 4. Delivering and unpacking data. And finally, 5. OSI versus the TCP/IP suite. All right, kicking things off with Section 1, the language of networks setting the standard. So how exactly did the tech industry actually solve that ultimate communication barrier between all these different devices? Well, it all starts with protocols. A networking protocol is essentially a logical set of rules that defines exactly how devices and software should play nicely together to communicate. But as you can imagine, to keep thousands of different protocols organized, we use networking models. Back in the late 70s and early 80s, the International Organization for Standardization, or ISO, created an open conceptual framework to categorize all these functions. They called it the OSI model. That stands for the Open Systems Interconnection Model. Moving right along to Section 2, the 7 OSI layers, anatomy of a network. We're going to look at the structure like a highly efficient, completely invisible assembly line where every single station has a very specific job to do. The OSI model actually divides network functions into 7 distinct layers. Now, trying to memorize them can be a little tricky, so engineers use mnemonics. If you read from the top, layer 7, down to layer 1, you can just use the phrase, all people seem to need data processing. That's application, presentation, session, transport, network, data link, physical. And hey, if you prefer going from the bottom up starting at layer 1, just remember, please do not teach students pointless acronyms. Now, what's really interesting here is how these top 3 layers act as the software side of things. This is the absolute playground for application developers. Layer 7, the application layer, provides the protocols that interface directly with your software. Stuff like HTTP for your web browser or SMTP for your emails. Layer 6, the presentation layer, takes all that data and translates it, compresses it to save space, and crucially, it encrypts it so hackers can't read it. Then, layer 5, the session layer, sets up the actual dialogue between 2 hosts. It establishes the connection, manages it with little checkpoints so you don't randomly lose your place, and terminates the whole thing when you log out. Right beneath all that software magic is layer 4, the transport layer. You can really think of this as the absolute heart of the model. It's the crucial bridge connecting your software applications to the physical hardware. It provides host-to-host end-to-end communication. Because data files are usually massive, this layer breaks them down into much smaller, manageable pieces called segments. But more importantly, it manages flow control and separates different traffic. Like, imagine you're streaming a YouTube video while simultaneously texting your friend on WhatsApp. It's the transport layer that actually ensures the video data goes to your browser and the text data goes directly to your chat app without getting completely mixed up. And finally, we hit the bottom 3 layers. These do the actual heavy lifting. Layer 3, the network layer, relies on IP addresses and uses routers to essentially select the absolute best path across different networks. Layer 2, the data link layer, deals with local node-to-node transfer using MAC addresses and network switches. And sitting at the very, very bottom is layer 1, the physical layer. This is the tangible stuff, guys. The physical cables, the electrical voltage running on copper wires, and the actual radio waves for your Wi-Fi. Let's jump into Section 3. Packaging data through encapsulation. So let's make this real. What actually happens when you send a quick snippet of video to a friend on Skype? Well, it all comes down to something called encapsulation. As your video data travels down that OSI stack, each layer wraps it in additional routing information, adding headers and sometimes trailers. This brilliantly illustrates the real-world equivalent of sending physical mail. Your data is the letter. The transport layer puts that letter into an envelope. The network layer puts the envelope into a delivery box, and then the data link layer packs that box into a massive shipping container. Let's actually move through this and see how it builds step by step. In networking terms, we call these packaged units PDUs, or protocol data units. It all starts as pure data up in the upper software layers. Once it hits layer 4, a transport header is slapped right onto it and it magically becomes a segment. Then it moves down to layer 3, where a network header containing that all-important IP address is added, transforming it into a packet. And finally, at layer 2, it gets both a header and a trailer, becoming a frame. Boom, the envelope is now fully sealed and ready to go. Which brings us to section 4, delivering and unpacking data. Okay, so our frame is fully assembled and it is officially ready to cross the wild physical network. Down at layer 1, the physical layer takes that completely packaged frame and translates it into raw binary data, ones and zeros called bits. And depending on your medium, the actual transmission completely changes. If you're plugged into an Ethernet port, those bits are sent as tiny electrical signals over a copper wire. If you happen to be on an ultra-fast backbone connection, they become literal pulses of light flying through fiber optic cables. And if you're just chilling at a cafe using Wi-Fi, well, those bits are beamed out as invisible radio waves. Now, once those physical signals finally hit your friend's target computer, the receiving machine does everything we just talked about, but perfectly in reverse. We call this de-encapsulation. The physical bits are magically converted back into a frame at layer 2. Then, the layer 2 hardware strips away its headers and trailers, revealing the packet underneath. Layer 3 looks at the IP address, confirms the delivery, and strips its own header to reveal the segment. Layer 4 removes its header, and finally, the pure original data reaches the application layer. And just like that, your friend sees your Skype video snippet. And that leads us to our final part, section 5. OSI versus TCP IP suite. Brace yourselves, folks, because I've got a massive plot twist for you regarding this beautiful 7-layer model we've just spent all this time studying. So the crucial point here is the OSI model isn't actually what modern networks use. Literally, no way, right? As brilliant as the 7-layer OSI model is, it's really mostly a conceptual framework today. The actual functional model that runs the modern internet is the TCP/IP suite. Developed by the U.S. Department of Defense through DARPA, the TCP/IP suite became the absolute undisputed industry standard just because of its raw efficiency and practicality. When you actually compare the two side by side, it's pretty cool. You can see how the TCP/IP suite elegantly compresses the, let's be honest, slightly bloated OSI model into fewer, more practical layers. The top 3 software layers of OSI, application, presentation, and session, are completely collapsed into a single unified application layer in TCP/IP. The transport layer, well, that stays exactly the same. The network layer simply gets renamed to the internet layer, and the bottom 2 hardware layers, data link and physical, are mashed together into one link layer, which is sometimes called the network access layer. It's leaner and highly functional. But here is the totally fascinating paradox of modern IT. Even though network engineers live and breathe in a TCP/IP world, they absolutely still speak the language of the OSI model. It's so true. When a website won't load because of a routing error, an engineer is never going to say there's an internet layer problem. No, they'll say, hey, we have a layer 3 issue. If a switch is acting up, they will instinctively call it a layer 2 problem. The OSI numbers have essentially become the permanent vocabulary of the entire networking industry. Which leaves us with a pretty provocative question to end on. If TCP/IP fundamentally runs the modern internet, will the OSI model eventually just fade away into obscurity? Or is its brilliant 7-layer conceptual structure just so perfect for teaching and troubleshooting that it'll be permanently hardwired into the minds of all future network engineers? Honestly, next time you send a text or load a web page, just take a second to think about all those incredible invisible layers working furiously beneath your fingertips. Thank you so much for joining me for this explainer, and keep learning.